Hello, everyone, and welcome back to Indigenes. We have had a short break and are back now with this brand new season on space exploration 2021 A New Dawn. Our guest today is the Chief Engineer of Robotic Operations for Mars 2020 Perseverance and the Assistant Section Manager for Mobility and Robotics Systems at NASA Jet Propulsion Laboratory. She specializes in space robotics, autonomous robots, and robotic operations. She has worked on a number of space robotics and artificial intelligence research and technology development tasks and has designed, developed, and operated rovers on Mars, the Arctic, Antarctica, and the Atacama Desert. She has been working at NASA since graduating with a Ph.D. in robotics from the Carnegie Mellon University and works on new space robotics capabilities from early design through development, testing, and launch. The Mars Ingenuity Helicopter technology is an example of the kind of innovation developed by JPL Robotics. Since 2008, she has been driving rovers on Mars, which includes the Spirit, Opportunity, Curiosity, and soon Perseverance. She is also a helicopter integration engineer for the Mars Ingenuity Helicopter. So as promised, we are now offering you a front row seat like never before to the Perseverance landing on Mars with our very special guest, Vandana Verma. So Vandy, from everyone here at Indian Genes, it's an absolute pleasure to have you on this podcast. We all know that this is a busy time for you, and specifically with the Perseverance landing coming up. So thank you so much for taking time out to speak to us, Vandy.
Thank you. I am looking forward to our discussion as well.
Great. And I think there are so many questions we have. The excitement is peak at the moment. We've been doing this online, getting a lot of questions. So I am also going to be putting in some questions that we've been getting from our listeners. But interestingly, let us start at the very beginning. And I have to start by saying you have the coolest job in the world.
Yes, I would say so. I really enjoy the work we do. And I often tell people that there's nothing I'd rather be doing than, robots in space.
And you've also driven all three rovers, which are the MER-A, the MER-B on Opportunity. The MER-A was Spirit and Curiosity as well, and now Perseverance. When you look back at this is an amazing achievement. How do you see it?
I see it sort of as a privilege too. It's really incredible to be able to have these rovers be our virtual presence on these planets. So when you're actually driving the rovers, you get really familiar with Mars, and it's like going to work every day, and you look at the pictures, and you're very likely going to be the very first person who's going to look at them, and not only look at them as something beautiful, but as how am I going to find my way through this path? So I've really enjoyed that, and every place is different. And every single day, there is some new puzzle to solve. So even though we might be doing in a broad strokes a drive or placing the robotic arm or drilling, each rock is unique, or each set of combination of things we do. And that's what makes it really exciting. So I really love the job. And the other aspect about it, which is really unique, I think, in terms of what we do, we tend to build machines that are unique, one of a kind. So you follow them from the development. So you're involved with parts of building the robot, and then you get to operate it. So by the time you're operating it, such as the case with Perseverance, in my case, we're getting ready to land. I've already been working on this mission for over 5 years. So you have that background of knowledge you bring to it. So I think it's that full spectrum of following the mission through its entire life cycle that I particularly really enjoy.
And coming to Perseverance, just the fact that we have put this whole mission together. When I say we, I think we're all involved in some way, but we have put this mission together that probably is the first time that we are going to be setting a stage to look for life on Mars or on another planet, right?
That's right. It's very exciting because our previous rovers really built up to this point. What Perseverance is going to do for the first time is we're going to actually be looking for biosignatures, which is signs of ancient life. Uh, the previous rovers, what Spirit and Opportunity helped us realize was that we proved that there definitely was flowing water on Mars. With Curiosity, we were able to find that Mars once was habitable. And now we are actually going to be looking for those biosignatures. In addition to that, what's really cool is we're actually, for the first time, bringing samples from Mars back to Earth eventually. And this is the first step of that process.
That is really exciting. And these samples that you talk about would be part of an upcoming mission or something in the future?
So the caching part we're doing with Perseverance. So what Perseverance is going to do is we're going to drill, and this time we're actually collecting intact cores, and we seal them in tubes, and we'll drop them off on the surface of Mars. There'll be another rover that'll launch, and that rover is going to go and fetch these samples. There's going to be a transfer step, but there's going to be another robotic arm that takes those samples and transfers them to a vehicle, which is the Mars Ascent vehicle, which is going to then launch from Mars and rendezvous with an orbiter that is going to take those samples and then bring them back to Earth. So it's an elaborate process involving global collaboration, and it'll be in the 2030s by the time the sample actually comes back to Earth. But what's really exciting is once we have the sample here, it'll be analyzed in laboratories all over. And as our science teams really likes to say is that the techniques we'll be using to analyze these samples, they haven't been invented yet. And the people who are going to probably be doing that are probably in high school right now. And so that's why it is so important to sort of engage the future generation, because they're very much a part of this exploration.
Right. And it's a continuous effort moving from one generation to the next. And just listening to you talk about it as a non expert, it just sounds so science fiction and very cool when you talk about you're going to be sealing it in a container and there's another rover going to be coming and picking it up. And all this is actually going to be happening on another planet. So that itself, just the thought of it and the audacity to do something like this is just amazing for the human spirit.
I think that's one of, like you said, what's cool about the job. So that's one of the most, I think, enjoyable parts of this job is you are both involved with the everyday aspects of the engineering of it, the details, the science of it. And then there's also what for the lack of a better word, what you might call the magic, which is you look up at the night sky, and when Mars is visible, you're like, there's a rover there that I know so well, and it's doing some commands and that I carefully planned out, and I know exactly what it's doing. So there's that aspect, which is the combination of the detail that you're very familiar with, and then the abstract, which is I think the inspiring part of these missions.
And one of the most inspiring part of these missions is the landing itself. A Mars day is 38 hours, minutes more than us.
It's about 40 minutes, so it's a little over 35 minutes, but we approximate it to 40 minutes. Yes, longer than an Earth day.
And it's called, so in a few sol days, we should be getting into the landing phase. And that itself is so exciting. Would you want to just briefly take us through to what's going to happen when we actually get ready to land?
Yeah, this is a really exciting part of a mission where all of the work that thousands of people have done in different aspects all kind of comes together, and it culminates in this very important moment where very shortly, actually, just even next week, we start the process of EDL, which we call entry, descent, and landing. So the spacecraft, after launch, it takes about 6 months, and it has been cruising to Mars. And once we get there, we start this phase where we have to enter the atmosphere and go from space all the way to the surface at a stop. Entry, descent, and landing is what it takes about 7 minutes, but it's often known as the 7 minutes of terror because there's so many things that have to precisely go according to plan in those 7 minutes. So when it's entering this atmosphere, it's traveling at a really high speed, and we fire our supersonic parachutes. And those parachutes, after the parachutes deploy, it slows down the rover, the whole vehicle, but it's still traveling at a really fast speed. Often you hear the analogy, it's like a skydiver jumping out of a plane without a parachute and going straight down at Earth. It's still traveling at that speed after the parachute finishes. And we then, the heat shield is deployed because when you're entering the atmosphere at those speeds, there's a lot of heat generated, which could damage the rover and the delicate electronics and instruments we carry. We have to further slow it down. We have retro rockets. There's 8 of them, and those fire and slow down the vehicle even further. And then the last step of it is we sort of have this jetpack maneuver called the sky crane maneuver, which is the rockets firing, and then it deploys the rover on a bungee cord down on the surface. What's really unique about Perseverance is that we really wanted to target an interesting spot, which is Jezero Crater. But it's a challenging spot because right through the middle of it, there is all these cliffs and dangerous features. How do you land in the spot very precisely? We have new technology on board. There's a capability called range trigger, which actually allows us to use measurements taken during the landing to fire the parachute at a particular time to allow us to more precisely land. And we also have another capability called terrain relative navigation. We're actually taking an image while we are hurtling through for landing, and we compare it to previous images in order to detect where we want to land, and we can do a divert maneuver. So that allows us to significantly reduce what we call the landing ellipse. So Perseverance is about 7 kilometers, and it is what's mind-boggling is this landing ellipse is 300 times smaller than what we did with the Pathfinder mission, and it's 10 times smaller than even Curiosity. So we were able to land very precisely because of these technologies. And this time, another part that I'm really excited about is that we will be able to share and see some of this. We have cameras this time that can look at the parachute deploy. You'll be able to see their cameras on the descent stage, which is the stage that is lowering the vehicle. There's also the cameras on the rover stage looking up at the descent stage. So you'll both be able to see the rover is separating away, and you'll also be able to see the descent stage. So we're doing this because it also gets us a lot of information for future landings we want to do eventually with humans. And then the last step of this, which is very interesting, is that you have to design this vehicle to actually be able to land on its wheels, which poses a lot of different engineering challenges. And then the descent stage, you don't want it to crash on the rover, so it then has to do a controlled fly away and crash landing at a safe distance away from the rover, so it doesn't contaminate the rover. So that'll be landing day, which is February 18th, and the time in USA that we get the signal from Mars, it's going to be about 11 minutes at the time, because the time varies depending on the relative position on Earth and Mars. So at 12:55 p.m., those of us who are going to be on the landing site when it lands at the control room at JPL, will get the signal to know that the rover has landed. And so that's a very exciting moment.
That's stunning. And all of us are going to be with you at the control room, at least in spirit and thought. So that's going to be an exciting moment. You said the landing would also capture video. Now, this video, would you all be watching this live or 11 minutes later, or does these signals come to you later? And when do we get to see it?
It's a good question. So there'll be, there'll be images taken that will be combined together. So actually, we do a couple of things during the landing. So we have the Mars Reconnaissance Orbiter, which is an orbiter around Mars that we've had for many years. In fact, a lot of the orbital images you see, even of the Curiosity landing site, and you may have seen images where you can actually see the Curiosity rover on Mars, taken a picture taken from the orbiter, was taken by MRO. We also have a Maven, which is also flies over the site. We do during EDL we do a bent pipe where we get telemetry soon after a landing, which will be 11 minutes later. But not all of these images will come down all at the same time. 10 hours later, there's a Maven pass where we will also get some additional information. So it'll be probably by the next day that we should probably have some of the synthesized images showing a lot of the imagery. But right after landing, we also take images from the hazard cameras. This is sort of something we've done with all of our rovers. And we have on the cameras at the time we land, we have covers. So the first images actually are with the covers on. So if you notice, they won't be as crisp, but they're the very first images. And as a rover driver and as a person who sort of operates the rovers, that is really the exciting moment where you're like, this is the location we're in, and this is what we're going to be driving off from. So those images come right away. After the 11 minutes, soon after, we'll be getting the hazard images, and we'll be able to see the area that we're in.
Sounds exciting. You mentioned about the last 7 minutes of terror. During these last 7 minutes, are y'all in control of what is happening, or would you have already pre-planned certain data points and given it certain commands? And are you able to do anything within those 7 minutes?
So, because of the time delay between Earth and Mars, the one-way time delay at this time is going to be about 11 minutes. It has to do everything autonomously because at the speed at which things has to happen, there is really no way for Earth to intervene. So by the time we hear back, it would have already have landed. So it's happening autonomously. We do prior to the EDL phase. There's a lot of like trajectory correction maneuvers and other details that happen, but that is the actual process is actually autonomous. It's not too different from pretty much everything we do on the rover. So even though when we drive, it's still very much the same, which is that the rover is going to be executing it, and we'll hear about it much later. But it'll already have happened. So yeah, it's going. We will have very little input into that.
Okay. And you mentioned the Jezero crater. That's interesting because part of this mission is choosing the right spot to land. And I guess one of the reasons for choosing the Jezero crater was because we think that about 3.5 billion years ago, there could have been river channels that were there at that spot. And we're looking for microbes, hopefully. But specifically, is that the reason we chose this particular spot?
Yeah, this is another really interesting aspect of the mission. The landing site selection is actually a process that involves scientists from all over the world that get together for multiple meetings over years to determine where to land. And at the early phases of this mission, those of us working on the engineering side, there would be big maps in our hallways of all of the sites that were still being considered. And you didn't know which one of them are the ones that you would actually be driving the rover on. But eventually, after many discussions and uh, weighing the pros and cons of each side, they landed on Jezero because clearly has some uh, really unique aspects to it. So Jezero is a crater where, when you look at the images, you can clearly see a channel as if water came through the crater rim all the way on the inside, and there was enough water that there was a lake. It's 45 kilometers, and there's a delta in the middle of it, and it's very distinct delta, and so that really makes it a place where we're very likely to find biosignatures of ancient life. And then we're going to be landing close to the delta, and we'll be making our way onto it. And then we're going to make our way from there onto the crater rim and following all the way out through there. So I think all of these aspects make Jezreel a very exciting place because there's such a high likelihood of finding what we came there to look for.
Mm. And especially for you, because once this does happen, then you take over, I guess, because that's when the rover comes to life. But specifically, the landing spot, if we try to understand that, I guess there would be some distance between where you perfectly want to land and then where you actually land. So, from your point of view, do you already have or planned or practiced different routes out of and into a different landing site?
Absolutely. One of the things about space robotics is that you really try to stay one step ahead and you think of all of the things that could happen. And this is a continuous process for every part of what we do. So, similarly, there's an ellipse, and we have landing dots that we place um, all over this landing ellipse as potential locations that we may land. And what's interesting about the locations is where there's enough variability as to what we might choose to do. And that's the important aspect of why we would pick one different site over the other as potential positions. And we plan what we would do if we landed there, if we landed on the delta, if we landed right off the delta. And based on that, how we would connect back up to the pad. Some of these locations we might take a little detour because we opportunistically landed in a particular place and we have the opportunity to do a scientific investigation in its proximity. Almost like Curiosity, where I remember when we landed, we intended to go up Mount Sharp, but there was this exciting opportunity to study Yellowknife Bay, and we ended up going towards that and made some of the most interesting discoveries in the mission as a result. So we plan these paths, but we stay very flexible because we're going there to make scientific discoveries. And by definition, because we want to learn about a place we don't know about. So we have planned paths through all of these possible places ahead of time. And there's actually an interesting you could call it a game that the team plays where all of us for the missions pick a little dot as to our prediction for where we'll land, and then it's really exciting to see who was accurate. Of course, there's a lot of guesswork involved in that because it's all part of the landing ellipse, but it's a fun process.
Amazing to hear, because I think you would be the expert in that. From what I know, you also developed a game to navigate through a maze, a robot navigating through a maze to collect balloons before you got into this, right? So I think that you're an expert now.
Oh, that's so interesting that you found that story. Yes, when I was in long back, when I took a mobile robot programming class, actually one of the first classes that got me really interested in robotics, uh, we did this really interesting thing in that class where they had us apply the theory to actually solve a problem at the end of the class. And I think this is a really good way to learn and to teach, where you apply that, you realize what aspects you still need to learn or what works. And the problem that we had was to have our robots autonomously navigate a maze to collect objects. And the rover that did it the fastest would win that. And it's very engaging. And my team ended up winning it, and we were so excited. And it got me hooked onto robotics.
And I think we knew at that time who the champion rover driver was going to be like. But Vandy, once this landing does happen, how long after this does the rover get activated? When does the rover move on, and what is that process then? When do you start getting directly involved and it comes into your frame of work?
So there are, there's hundreds of people involved in the operation. So, it is certainly, I'm a small part of a very talented team. Both on the entry, descent, and landing side, there's a lot of people. And then we hand over to what we call the surface side. And that's the part I am on. So it happens right after landing. There is a handover from EDL to surface, and the surface team takes over. One of the first things we have to do is actually talk to Earth. So we deploy our, we do a check with our antennas. We also deploy the mast of the rover. So when we are landing, the rover really has to fit in a very tight space. And there's a lot of robot origami involved with how we fit things in, and they're all tucked inside. The wheels, of course, deploy during the landing phase because this rover lands on its wheels. But after landing, we deploy the mast, which has the cameras on it and some science instruments on it. We also then do a checkout of all of the various aspects of the engineering. So we have days we're going to steer the wheels. We will do a short drive. We will calibrate all of the various instruments we have. We will deploy the robotic arm. When we land, because of all of these dynamics that you can encounter during the landing and actually even during launch, a lot of our components, such as the robotic arm, are actually attached through launch locks of special mechanisms, which are different from what we use on a daily basis when we stow the arm. And we have explosive devices that we fire to release these and start operating them for the surface operation. So all of that has to happen. And there's a series of these that will occur day to day. And we have specialists on each of those days who will be operating the different activities together. And so after that all happens, on this rover, we actually have another special phase that comes into the picture, which is that we have a helicopter. And we will be deploying the Mars helicopter and doing the Mars helicopter flights. And then once that phase is over, then we'll be moving into the surface operations phase, where we move into the scientific investigation and start driving and analyzing the samples and collect them and sort of get on with the science exploration part of the mission.
Right. So you mentioned that you would be sending certain commands for the rover to start moving or for the wheels to start moving after you've deployed totally. Now, these commands, I guess, as a person who's operating the rover, you would have to keep sending multiple commands, because once a command is obeyed, you do not want it to wait for that 11 minutes. I don't know how long it would take for a command to get there. And I guess you would use the deep space network, right? But you would want to do something much in advance. Is that how you would go about it?
You're absolutely right. We don't want to slow the rover down by sending one command and then waiting for it to the response back to that and send the next one. We would make very slow progress that way. During the early phase of the mission, we are on Mars time, but there's still the light time delay between Earth and Mars, just because of the relative distances between them. At the time of EDL, this distance is about 250 million miles, but at different points, it can get up to 350 million miles. So you don't operate it that way. On the moon, we sometimes do it that way because the time delay is much lesser. But on Mars, we send all of the activities that'll occur for the entire sol. And even though we are operating in Mars time, where we will get the data back soon after when the rover finishes executing it, we still want it to do all of those activities, which makes it really interesting. You have to think about all of the things that could go wrong proceeding to every command. So if I'm driving and I am trying to get around a rock that is 10 meters away, if I encounter slip, which is essentially that the wheels are turning in place but not making progress, and I'm short, could I turn into that rock? I have to compensate for that. I have to put in checks in place such that I am sure that we are at that position by the time you are trying to make what we call a dogleg. So we do a lot of what if thinking, where we think about all the possible ways in which the preceding commands may result in execution that either fails or it executes in ways that are slightly different from the way nominally we expect them to, and we compensate for it. So that is something which is very much an aspect of Mars operations, and I think that makes it really interesting because you have to try to imagine what would happen. We have a lot of tools that help us do this, and so a lot of the process is sort of been refined over the many years we've been operating rovers, all the way since Sojourner, and so we are able to do this very precisely.
Interesting. And for a long mission like this, Vandy, uh, do you have phases in driving? And does it move to autonomous driving when you want it to? Or are there different times when you would want to go specifically to a destination if you find something interesting and you decide to take a left when the plan was to go straight? Does that happen?
So there's, you bring up a lot of interesting aspects that when you're not in the driver's seat, how do you also make sure that you're not missing, really interesting features as you're driving? There's a term that we use, called the dinosaur bone, which is essentially, saying that you found something very interesting that you would not want to miss. So we do try to make sure that we don't do that. And but at the same time, we are pre-planning that. So when we're doing a drive, often what we typically get is we get images from Mars. These are taken by navigation cameras. These images are in stereo. We have two eyes, so they have essentially what that gives us is depth perception. So we can actually see distances and we can see in 3D. So as rover drivers, we put on our 3D glasses, and it's very immersive. So you can actually see the terrain pop out, very different from seeing sort of a flat image. It's the computers on the rover are still much slower than what most of us have sort of on an everyday basis, and so we have to think about the computation that we are doing versus the utility of it. So when we are driving initially, we tend to have the rover drivers pre-plan where it's going to navigate carefully for as far as we can see. And we can see, very well, even up to about 70 meters and beyond. And so we'll drive very fast through that area. And then beyond, when we can't see beyond the horizon, we'll turn on our autonomous navigation, which then takes the subsequent images beyond where we would see onboard, does analysis to figure out where the hazards are, navigate around it, and continue to drive. Perseverance is going to be able to drive a lot farther than the previous missions. So currently, the planetary record for driving in a day is Opportunity, which is about 214 meters in a sol. But Perseverance is going to do an average of 200 on every sol. So it's really going to be driving a lot further. And then the other aspect of the question you asked is, how then do you, not miss some of the things that you might encounter? We actually also on board have a lot of autonomous intelligence that we put on board the rover. One of the things that I worked on for Curiosity, and we have um, uh, an enhanced version of that on Perseverance, is called Aegis, which is a capability that allows the rover to autonomously take a wide angle image and then in that image look for interesting features. So in that image, it'll automatically try to find what's an interesting rock or what's an interesting feature. These are all based on what scientists pre-specified. And they can change that. If you're driving through a terrain where we are expecting to see a lot of sand, it might change what they're looking for. If you're driving through an area where there's a lot of bedrock, they may change that. But they specified what they think is interesting, and it'll look for that. Once we find that, we are able to then point you know, uh, high resolution instruments such as the SuperCam on it and shoot the laser to autonomously take measurements of the interesting features and then transmit them back to Earth at the end of the drive. So along the way, we do have capability such that we can opportunistically take measurements of interesting things.
That's so cool. And I think Sherlock is also something very similar to what you were mentioning, because it sounds very cool when you hear about the spectrometer and a laser for a camera to hunt for organic minerals. Something similar to what the SuperCam would do.
So the SuperCam is on the mast, and what's nice about SuperCam, right, is it can take measurements, what we call remote science. So essentially, when we drive up to a place, we don't have to deploy the robotic arm. You can take a measurement up to 7 meters remotely. It has a telescopic camera, but it also has this ability where it targets a laser to a rock, and then when the plasma comes out, it is able to analyze that and based on that, study the composition. In fact, on Perseverance, for the first time, that there is also attached to the SuperCam a microphone. So when that happens, it can listen to what is believed to be might be a popping sound that happens when the plasma is when we shoot the laser at the rock, and that'll provide additional information. Now, Sherlock is an instrument which is at the end of the robotic arm. Now, the advantage of that is you can deploy it in really close proximity to surface targets and get really good measurements that way. And so that also um, uses, Raman spectroscopy and provides information of, rocks that we are able to get a really high resolution. In general, because it's so important when we find biosignatures or looking for life on other planets, we're very much looking for correlated observations. And that's why we carry these suites of instruments. You want to have multiple confirmations that tell you that your hypothesis is correct. And so all of these instruments together play a role in that.
That's so interesting. I was just thinking of when you're talking about driving a rover. So for you, you've got to be really aware that while this is happening, or Sherlock is doing his action, or specifically, I was thinking about the robo arm, which is either extended or performing something. You've got to make sure the parking brakes are on.
Yes, yes, yes. So I think at the end of every drive, we very precisely try to get workspace information in front of the rover for deploying the robotic arm. So there's an entire set of coordinate frames that we have to populate to know exactly with respect to where the rover is, where the target is, and how we're going to position the robotic arm. So you could hypothetically, sort of call it putting the parking brakes on, but we stop at a particular spot, and we have a whole series of things we do in order to take those measurements. So one of the things that happens at the end of a drive when we're ready to deploy the robotic arm is that we're looking for targets that are interesting in the workspace image, and we need this image to come back to Earth. But we also have the capability to deploy the robotic arm on this mission, and we'll be able to take an image with the Watson camera, which is sort of a hand lens camera at the end of the robotic arm, so we can get high resolution images and transmit them back to Earth at the end of a drive, which will also provide additional information to the scientists to be able to decide where to take measurements with Sherlock and Pixel.
So I was just thinking about this when we spoke about the driving on Mars, which is very exciting for us as non-experts, because here on Earth we drive fast, slow, reckless, and careful. I guess those are 4 ways of driving that I know of. Could you break down what are the different techniques that you would be using as far as driving a rover is concerned? So I know the first one is something to, is it called traverse, if I'm not mistaken, where you have a specific destination?
Yes, so there's a lot of different ways in which we drive, and none of them are reckless, or so we hope. In general, yeah. So I think in general, the driving is not terribly fast, and part of the reason is that the speed is not what matters. It is sort of the accuracy where we are getting at things. So the rovers actually drive at 4.2 centimeters a second. It's like the absolute speed. But we have different modes in which we drive in order to make progress toward our destination at different rates. So there's a part of driving where we are traversing, as you were saying, which is where we're trying to cover large distances and get to another interesting location. So say, we were done observing the delta and we are trying to get to the crater rim. We might decide to do a traverse, which is that we're mostly interested in covering large distance to getting to a particular area. When we're doing that, we try to drive as fast as possible, and we do the blind drive to as far as our imagery shows us, and then we turn on auto nav, and for as much energy that the rover has, we'll continue to drive till the next, what we call the decisional pass, which is when data comes from the rover to Earth. And that just gives us an opportunity to mid-course correct in case there's information that comes out that makes us change our plans. Because we're going to a place that no human has ever seen before, the information we get might alter what we want to do. So that is kind of one of the ways in which we drive. But the other ways is where we are very interested in doing targeting at a particular location, and we want to say drill or place an instrument. And so we call that a precision approach. So once we get to a particular location, we might look at images from our high resolution cameras. There's science cameras, the Mastcam Z on the mast, which also has zooms. And there the scientists might precisely say, I want to get to that particular rock, and I want to get to that feature on that rock. And this can be on the order of, like, say, centimeters. And so we are then doing a precision approach and driving the vehicle such that we position it to be able to target it. What's really interesting with the precision approaches is you're not just trying to get to that location, you're also trying to make sure that you can deploy the robotic arm with all of its constraints on it. We have a 5-degree freedom arm, but it's not arbitrary what we can get to. There's a relative position of the rover and the robotic arm you have to consider. And we also take into account all the possible things we might want to do there and whether all of those are possible at the altitude at which you'll end up. And then the other part of what we do is a walkabout, where we sometimes do a circuit around where we are taking measurements with our remote cameras. One of the other types of driving we do is what we call a walkabout, where the scientists are trying to pick the most interesting specific spot in a region where we want to do more detailed investigation. So we'll do a first drive where we kind of just taking the equivalent of pictures, or we might use the we will use all the various cameras, and we also used remote science such as the SuperCam. Once we've done that in a few locations, then we come back and say, I'm going to deploy the robotic arm and do the next expensive. And expensive in this case is in terms of energy and time. Deploy the robotic arm and maybe take measurements with the Pixel and Sherlock instruments. We will do that then at the down selected locations that we have in this particular area. Then finally, we pick from that the most interesting location and go back to that, and we would deploy the arm and then drill there, which is the most expensive in terms of resources and time, and collect that core, where we are now dedicating one of our 37 potential cores that we're going to collect to that location. So that's another type of driving we do.
Very interesting.
And there's another aspect of the types of driving, though, which is how you might try to, from a robotics perspective, navigate through a terrain. And that's where the rover driving team will make a call. One is where we are driving using the imagery that the rover got, planning precisely how far we will go, where we will turn, and what sort of corrections we will make along the way. What we found from having been on Mars for so many years, some of us have been driving on Mars for over a decade, is that Mars is a really sandy place. And in general, because there are no roads and we're driving on free-form terrain, we encounter what is called slip. So the wheels are turning, but they're not making forward progress. So encoders are telling us that we're moving, but as happened with Opportunity at Purgatory, it made downward progress up to 40 meters in Opportunity's case, where the rover can then get embedded or stuck in the sand. We have since developed technologies that allow us to correct for that. So now, because there's no GPS, we can't just use position estimation based on that. We take visual estimation. So we take a picture, and then we command the rover to move, and we know how much we commanded it to move, and we take another picture. And then we use vision-based techniques to do image deferencing to see how much a rock we saw in that first picture moved in the second picture. How far has it moved? And if it hasn't moved sufficiently far, then we know we haven't gone anywhere. So that's another capability we have, which we call visual odometry. And odometry being, the odometer where we are taking distance, this is visually doing that. So that's another thing we can turn on. We have, over our rovers, improved the technology so much that it's now really fast, and we don't have to think about doing visual odometry. On Spirit and Opportunity, it took 3 minutes to do a visual odometry step. On Curiosity, it took about 30 seconds. But now it's going to be so fast that we will just have it on all of the time, which allows us to prevent these situations where we are, driving in sand and not making progress. The other mode then we have is this autonomous navigation, where we let the vehicle decide what path to navigate. So we just pick a dot somewhere and say, this is the destination that the science team's interested in going. And the rover takes images with its cameras, analyzes them from hazards, and drives. But there is actually a lot of element of configuring that. For those who might work on self-driving cars are well aware that you still have to alter the parameters of what you are asking the rover to do. And there are things like, what is the step size? How frequently should it take the image? How should it take the images to build the map? There's various aspects of it that you still have to think about. We also try to demarcate areas which are definitely don't go here or definitely stay within this region. And we call those keep ins or keep outs. So that is also something rover drivers do, even for autonomous navigation, helping it based on ground-based knowledge we have from orbital imagery, to say these are locations I know you shouldn't even bother attempting to navigate around because it's too hazardous, such as a crater. And so those are really the main modes of driving that we use. And a lot of what rover drivers will do is to pick which combination to utilize for a particular drive.
So you do pick that, and you were mentioning about the already defined paths. I think that would be called the global path, right? And versus local driving, when you take over, does that depend on some data that has come to you, or a reaction, or who decides when you move from autonomous to manual?
So so we typically don't move from autonomous to manual very often. We usually do move from the manual to autonomous. And the reason is because in order to do manual, you need to have images of the region around you. And that typically is at the beginning of the drive because you have the images from the previous drive that the rover took and came down to Earth. And then you turn on the autonomous navigation. That is done entirely by the rover drivers to decide which part of it we want to do manually and autonomously. It is based a lot on the time and energy available and when the orbiter passes will come. So it is very much a coordinated effort with the entire rover team, the surface rover team, because you have to have enough energy on the vehicle in order to drive that distance. You have to plan when you're going to heat the motors. You're going to have to plan when the orbiters are flying over the rover such that you'll be able to transmit the data, and you'll want to have ended the drive by that. So even though that technical decision is there, the rover is part of an entire spacecraft system connected all the way to Earth through the orbiters and the Deep Space Network, and it requires coordination of all of those elements.
And you did mention that there's been a lot of advance in the driving tools, I guess, since Sojourner. And what about how different is the drilling that we're talking about now compared to Curiosity? Is Perseverance, is there any change to the drilling techniques or specifically anything new that's happening there?
Yeah, that's a great question. Even though we are drilling, there's so many different ways in which you can drill. And the drilling is quite different. The drill is still at the end of the robotic arm. So we have at the end of the robotic arm what we call a turret, which has all of the tools and instruments. And the turret just keeps getting larger and larger with our rovers because we are carrying more and more instruments and tools. And so the Curiosity turret is about 30 kilograms, but the Perseverance one is about 45 kilograms. So there's a lot of instruments we're carrying at the end of it. The drill being one of them. The difference between the Curiosity and the Perseverance drill is the Curiosity drill is a rotary percussive drill. So it's essentially like a hammer drill which powderizes the sample. So as it's drilling, it's generating powder that we ingest in, and that powder transfers from the drill into another compartment on Curiosity, which is an instrument called the Chimera, which has a number of compartments to sieve and process the sample and deliver it to instruments such as SAM and CheMin in the belly of the Curiosity rover. On Perseverance, the drill is a coring drill where it is collecting intact cores because we want to bring them intact all the way back to Earth. So the drilling technique does have some percussion, but we can just use the rotary aspect, but mostly to get through the surface. But it's collecting an intact core. The way we do it is also very different. What's really exciting in Perseverance is essentially we've combined what would be a number of different tools at the end of the turret, making it even heavier. And mass to space is one of the big aspects you think about in terms of space robotics. Is you're really trying to reduce that because you have to pack it all onto a rocket, and it has a weight limit to launch. The drill is operated through a mechanism we call bit exchange. So we have a number of different bits that we can change into, sort of like switching out, and use those on the drill, on the surface, to do different things. So there's an abrading bit where we place the abrading bit on the surface, and we can abrade the surface, so we create a spot that is flat enough, because the instruments such as Sherlock and Pixel need a cleaned out surface, which allows them to take even more precise measurements. The drill can switch that out and switch it to the scoring bit, which collects the intact core. It can also switch out to a regolith bit, which allows us to collect a soil sample. So we've sort of combined these multiple tools into one drill, which is a very different aspect. And as a result, the drill has to dock onto a carousel, which is on the body of the rover, both to switch out these bits, but also to take that core and deliver it to the inside of the rover. There's an entire robotic assembly on the inside of the rover with a second robotic arm that takes that core, and then it's handed over to the second arm, which we call the SHA, the sample handling arm, and that then does a number of assessments on the inside, which does a volumetric assessment. We take a picture of it, and then we seal it. So the drilling mechanism is sort of tied in with all of these aspects.
The more I hear of this, the more curious I become and the more amazed I am. Absolutely. It's just such a stunning experiment. You mentioned about the drill. Uh, as far as the rover itself is concerned, and something that probably directly affects you, are the wheels anyway different this time compared to what either Curiosity had or Opportunity? Because I know it was the Dingo Gap, right, where we moved into a sand dune. And did we take any lessons from there and actually change something as far as wheels are concerned, or something as small as wheels are concerned?
You're absolutely right. We did change the wheels, and one of the things that I'd mentioned earlier is it's challenging to design wheels that both allow you to land on the surface on the wheels, which requires some amount of compliance in order to do that, and also have wheels that can navigate on all kinds of different terrains and are light, because you don't want to spend a whole amount of mass on those wheels. So these are a huge number of factors that come into play. And Curiosity's wheels uh, had, we have 6 wheels because we have a rock-a-bogie suspension system. So we have the 4 outer wheels of the rover, the 2 front wheels and the 2 rear wheels. They're both steer and drive wheels. The middle ones are just drive. And the rock-a-bogie suspension system allows the rover to climb over rocks, that are much higher than you would otherwise be able to do, while keeping the body and the instruments flat. So unlike a car, which if you drove over something, the entire car would tilt, the rover sort of just has its suspension and the wheels go up, but the body, to some extent, will stay relatively flat. The wheels are different because as we were driving along with Curiosity after landing, the rocks we encountered were much sharper and a different composition than had originally been predicted. And we ended up finding that they were resulting in little tears on the wheels. And that made us actually, as you mentioned, detour from the path that we were taking as we were going towards Mount Sharp to find better terrain. And to do that, we actually ended up climbing over Dingo Gap, which was our access through Moonlight Valley into terrain that would be sort of more gentle on the wheels. On Perseverance, taking the lessons from those meals and spending a lot of time, we did a lot of live tests where we drove these wheels around in the Mars yard to analyze what was causing that impact and how we could compensate for it. The wheel design that we have has wheels that have a different Grouser pattern. So the Grouser pattern on Curiosity had like a chevron pattern, which created stress points at those triangular intersections. Whereas on Perseverance, we have more of a waved pattern uh, for the wheels, for the Grousers. And the wheels are also slightly thicker. So we did invest a little bit more mass in the wheels for Perseverance. So that's some of the change that we've made. They're still the aluminum wheels that we've had machined out of, a single block of metal, and the Grousers are titanium. So that's still similar, but the wheel pattern and design is slightly different.
Interestingly, you just mentioned in passing something about the Mars yard, where you said that we tested the wheels on this Mars yard. Is this Mars yard a location, an actual physical location, or is it virtual?
Oh, that's a really great question. The Mars Yard is an actual physical location at NASA's Jet Propulsion Laboratory, uh, up the hill, where we have a place where we create terrain that we can simulate a lot of the conditions that we want to test. And we have the rovers that we drive onto various different types of slopes. We have flagstones. I've created little sand traps there where we've had to test the rover for such as scooping soil, or doing different things with the robotic arm and positioning instruments. We use our full-scale Earth replica of the rovers that we build for pretty much every rover in the Mars yard to test in sort of these natural conditions. Now, what's different is gravity. So Earth's gravity is obviously a lot higher than Mars' gravity. So we also have a second vehicle uh, that we have, which we call the Scarecrow, where we stripped away the mast and the arm so that the weight of the vehicle on Earth is equivalent to what the full vehicle would weigh on Mars. What this lets us do is test with the actual ground pressure that the real vehicle would have on Mars as we are trying to navigate some of these challenging terrain. So we have the vehicle system testbed, as we call it, the full vehicle, and the Scarecrow in the Mars yard. We also, for the wheel test, had a mechanism set up where we just had wheels at the end of this long boom arm, just driving around different types of terrain that was there over a long period of time, months, to do some of this testing. So it's a very reconfigurable space that we reconfigure for whatever experiment it is that we want to do, which is the Mars yard is different from the indoor facility we have. So we have facilities where we test indoors that are cleaner for different other aspects that we need to test. There we then have to simulate natural light. And so we have a lot of lamps on the inside of it, and we can reconfigure that in different ways as well, which is also different from another test facility we have where we have just the avionics, where we have racks and racks of the computers that would be on the vehicle. We can attach certain instruments and other simulated parts of rover hardware to it to then test sort of the brains of the rover and the software. And then, of course, as you mentioned, we also have purely software simulations in which we can test various aspects.
That's really interesting. And that obviously my next question is, how do you train a rover driver? And do you have some kind of certification, simulation? How do you make sure that no one bangs into the Scarecrow at the Mars yard?
There's lots of different stages of training a rover driver, both in terms of just the stages of training, but also different times when the training is different in the life cycle of a mission. So in terms of driving in the Mars yard, we have a number of engineers who work really early on designing the requirements for the vehicle and have spent a lot of time thinking about it well before by the time we actually are operating in the Mars yard. The advantage in the Mars yard is you're right there. There's no light time delay. So we have what we call a kill switch. So this is very special only for Earth, where when we are testing the vehicles, uh, those who are operating the vehicle have the ability to hit that kill switch if something unexpected happens. So that's the advantage. It's also more necessary early because we're literally just doing things for the first time with the vehicle and testing things out. And by definition, you want to push the envelope and you might discover something unexpected happens. So that's our safety. And a lot of the people who work on it at that stage are working on the design and development of it. As we start to move into the operations phase, generally in the early part of driving the rover, a lot of the rover drivers, such as on Perseverance, all have a lot of experience from uh, developing the rover, involved in various aspects of the design, the programming, and the engineering of the hardware and various other aspects of it. So come in with that knowledge, which is very important when we first land in a new location. Even if you might know the vehicle on Earth, there's a whole phase right after we land to understand the system as it interacts with its environment as an entire system, which is part of the driving. It's connected to the entire spacecraft. And for that, we do training in simulation where we have images that we take from the Mars yard, and you can plan drives. We have things that are called operations readiness tests, where the entire team comes together and we simulate what it would be like to be on Mars, but we're actually driving in the Mars yard, the vehicle. We also do thread tests where we are testing specific just driving aspects with a slightly more local aspect of the team. And so these are sort of different ways in which we train in simulation and in the Earth test environments. Once we land, we start very quickly to train new rover drivers. And there's both classroom training of the aspects of the different drive modes, what to think about, and the engineering of a specific rover. But there's also shadowing, as we call it, where they sit alongside somebody who's actually the prime and follow along, initially just observing and then being hands-on and driving, sort of like you do for flying an airplane. You know, those of us who fly airplanes start off with an instructor initially, and you gradually move on to being the person in control and the instructor turning to the observer. So that's very similar to kind of how rover driving works out. What's so interesting as the missions go on is that the next generation of the rover drivers then train the subsequent one, and it goes on and on. Because by the time we have another rover landing, a lot of the people who would have been on the previous rover might have moved on, and the entire team, for example, on Curiosity, is a new generation of rover drivers, while a lot of people are operating Perseverance, and similarly happened with Opportunity. And the reason is you can't be on Earth and Mars time at the same time when we land a new rover. So even people who might have been working on both missions end up switching over entirely to the Mars time mission.
These particular skills that are required, those are the technical skills somebody needs to be some part of the engineering mission. Do you also look for certain behavioral or conceptual skills for people to react under stress situations like we would do in any other job?
That you bring up a really important point, which is important, I think, in general in all of the engineering that we do, is when you're working on a mission, what's a hugely important fact is you're working with a team. None of this, that we talk about it as we are doing this, but it's actually specialists in each of these different areas together. So as a rover driver, you're part of a team, and that's a very important aspect, is somebody who can interact with the other experts in the room. There's a thermal expert, there's a communications expert, there's you're trying to together get the spacecraft to do the drive. So that's an important aspect, and also be able to weigh how important it is to do something under the clock, because very much you have to transmit the data to the spacecraft by a certain time. At the same time, being confident enough that if you're not comfortable, even if there is a deep desire, because this is so important scientifically, you say, no, we can't do this until we do these checks. So you have to have the confidence to say that, but have done all your homework to make sure that you're doing it for the right reasons. And then also, be able to work, as you said, under the time pressure. So it takes a combination of those skills, and also really enjoy that. Like, thrive on the aspect of having a challenging problem and trying to figure out everything you can to make that drive succeed in the time allocated and to be able to focus on it.
Definitely, those are interesting components of the job as well. And does this culminate or end in some kind of certification? For example, we were talking about flying. So we talk about something like a private pilot license or a commercial pilot license after certain hours. Do y'all have something similar where you can actually obtain a Martian driving license or a rover driving license?
Actually, on Curiosity, they gave us a little driving licenses, which was kind of fun. We do have certifications. So generally, uh, different missions adopt different strategies for what the certifications might be. On Curiosity, there was a different certification for driving, for operating the robotic arm, and for sampling. On certain missions, you need to do both in order to certify as a rover driver. And it's a long process. It can take, in certain cases, years to train a rover driver in all of those aspects. And once you're certified, you are then certified to be prime on the seat. There's always two pairs of eyes. So on any particular drive, we always have two rover drivers, the rover drivers working together on the sequence. And it's a very well defined what aspects they work on. The initial rover driver will plan the path, set out the initial moves. They work together to discuss what the trade-offs would be, and then there's a discrete handoff where they walk through the entire sequence, and the next rover driver is then responsible for the sequence and communicates it to the team, and then generates the sequences and goes through all the checks such that it will be radiated to the spacecraft. So the training involves knowing what all of the checks we do in all of those stages are, understanding all of the different aspects of not just the driving, but the interaction with the rest of the system. For example, if the robotic arm is unstowed, we don't drive with the arm unstowed because it would add a lot of different challenges. So we stow the arm. So understanding that, what are the checks? How does it interact with the rest of the system is very important as well.
Right. And two of the drivers together, do y'all also have some kind of time restriction?
The entire day. So when we plan a particular sol on Mars, there's a very well-defined milestones along the day of what needs to happen by when. And it's a coordination with the entire team. We start the day with the science team actually deciding where we'll go, because it's based on data that came down and what scientific investigation we want to do. In addition, if it was a day where we were going to deploy the robotic arm, the science team would be picking specific targets on which they want us to deploy the robotic arm. Once that's decided, then the rover drivers will go and analyze from the engineering aspects whether that target is reachable or whether we need to sort of adjust the orientation by which we approach it. Or when we are driving, if we want to look at doing things slightly differently or target a slightly alternate location. And then you coordinate with the science team. You go back to the entire room of people who are planning the sol and show an animation of the drive. And then there's another step in which you go back and connect it with all of the sequencing that has to happen, all of the other activities, and do all of the checks and communicate that to the team. And there are all these timelines for it. And the reason is because while you're working on the drive, if you along the drive want to take measurements with another instrument, those sequences have to be integrated such that they interact in the right manner with the vehicle. This is particularly important when we are positioning the robotic arm, because when we place the robotic arm, we are then going to maybe do a Sherlock observation. And the Sherlock team would be very carefully planning out all of what they'll do there. For example, there's aspects on instruments that can be managed differently depending on what location we're going to. We have an instrument, the pixel instrument. That instrument is at the end of the robotic arm, and we have to position it within centimeters off the surface. But the robotic arm itself has contraction because of the thermal changes. And so overnight, when it's doing observations, it might actually move. So at the end of it is a hexapod. There is a mechanism that allows it to take images and correct for that using the hexapod mechanism. Now, when you're positioning the robotic arm, you have to think of all the ways in which that hexapod might move and adjust so it's still safe and doesn't collide with any part of an adjacent rock to what you're observing. So these are all the things that you would have checked, gone back into the timeline, communicated to the entire team if you needed to make an adjustment, make sure that that adjustment still meets the science objectives for that sol. And then at the end of the day, all of it has to be combined into a bundle such that it's radiated to the spacecraft. And the reason the checkpoints are so important is there's some other team that's analyzing how much power the vehicle has. If you do some different activities, they might actually take more energy, and we might have to have the rover take a nap in the middle of the day, as we call it, to recharge and adjust for that. We also have to make sure that the data that we are sending to Earth is the size that it can be sent through the orbiters to the Deep Space Network to Earth. All of these things together are being worked in parallel. So you have these checkpoints along the day, which are very definite timelines by which you have to have certain aspects ready so that everybody can get the information they need to do the next round of their job. And at the end of the day, the really strict deadline is the time at which we have to send the commands from Earth to the rover, because that it really is the deadline. And if it's not ready by then, you actually miss a sol. So that's a very important aspect. So we communicate the commands from Earth to the rover, and then we transmit the data because there's a lot more of it from the rover to the orbiters around Mars, and from there to the Deep Space Network and back to us.
And you mentioned that a specific test, if it had to be done either by Pixel or Sherlock or SuperCam, which was not planned, you mentioned specifically that we needed to conserve energy because otherwise you would have to stop or sleep out for some time. And I know Curiosity had about 133 megahertz processor, but Perseverance would be much more now compared to what Curiosity had.
We actually also have 133 megahertz processor. We in fact have two similar to Curiosity. Both rovers have two computers. One is a prime and one is a backup, which allows us to switch. In fact, we've done that multiple times on Curiosity, where we've switched computers because of various faults. In addition, has a third computer, and this is what really allows us to drive so much faster. So we have a third computer with an FPGA that allows us to do hardware-based image processing. This both helps us actually during EDL. So when we're doing entry, descent, and landing, this computer called the Vision Compute Element, the VCE, is allowing us to very fast process the images such that we can do that correlation we need to do the divert correction. Once we get to the surface, we put it to good use for the driving. We can using this dedicated processor, we are able to do that computation of the hazard avoidance on board, like to do the image processing to know what the hazards are very fast. And we're also able to do that visual odometry. The reason we're able to do that checking of whether we're getting embedded in sand traps very fast is because of this extra computer.
When we talk about driving with precision, comparing it to driving here on Earth, the last thing any of us want driving here on Earth, because that's the only experience we have, is for someone to run across or jump across, or something to run across or jump across your vehicle at the last moment, unexpected. But in your case, that would just be amazing and a history changing moment. But have you had, not so dramatic, where somebody has ran across a rover, but have you had any interesting experiences on all your drives that you would want to tell us about, and something we don't know?
It's interesting to think there's something interesting that happens every cell, literally, because it's interesting to think about that no robotic arm positioning or drive, every aspect of the spacecraft goes precisely as you predict, because there are so many elements and there's so much uncertainty. But we account for that uncertainty, so we know we're within the envelope. But in terms of really interesting moments, there's so many. Gosh, I have to try and think about which one I would pick. But it was on, I guess, opportunity. We were driving along, and we were mostly driving in Meridiani, where there was mostly just sand everywhere. And you're not expecting to see too many rocks. But at the end of the drive, we came across this beautiful rock, which was a meteorite that had fallen onto Mars, called Block Island. And we ended up spending considerable time investigating it. And I think that was really interesting, because you even though you might have been driving for months in terrain where there's no change and there's mostly sand, you can at any time have something unexpected happen. So that is the thing that rover drivers do, right? You're always assuming there could be this hazard, unless the data indicates otherwise. So, I always remember that. And then we always have new technology that comes in because of something surprising that happened. And we almost drove right, very close to another meteorite, because we discovered that our cameras had certain amounts of a range error at a certain distance. And I think that's another aspect that we then started compensating for. So, that was early in when I was driving the rovers. And so I really remember that.
Just wondering if somebody is looking at the images as the drive is happening. So these images would be picked up by your computers. If there's a person sitting and monitoring a screen to look at what's happening outside, any form of visual anomaly, would that be picked up by a computer, or would that be picked up by a person? And when I say visual anomaly, I'm looking at something that should not be there.
Both. If we see something interesting, um, we have technology on board, such as the Aegis intelligence I mentioned, where we take images and we are analyzing the images for an interesting feature that we might target autonomously with the laser. That would happen on board. But we also get the images down on Earth, and there's some image processing that happens. But there's also a lot of scientists looking at the images from the perspective of science to find what's scientifically interesting. And then there's engineers looking at it from the perspective of what's interesting engineering wise that we want to observe. Where we have observed, for example, when we landed with Curiosity, one of the first rocks that we positioned the robotic arm was on Jake Matievik. And there was a contraction overnight such that, a contact sensors disconnected and then connected again. You might observe that uh, uh, change both visually and in the data. So, we are always looking for things like that at every part of the project.
And specifically with this Perseverance mission, Now, Vandy, you're going to be busy over the next few months, I guess. And technically, 1 year is the duration where this mission has been set up for. But we do note that from past, as far as Curiosity is concerned, or the other missions, it has gone on much further. Now, what are your expectations from this, Vandy, and how positive are you that whatever we've set out to do, we will definitely be achieving that?
So one of the things in space robotics is there really are no guarantees, but by the time we launch and land, we have put in so much um, sort of engineering into it that we are pretty sure that we've checked all the boxes we'd want to check, and are fairly confident that we've tried to do the best we could to try and make the mission succeed. So I'm really looking forward to this mission. There's so many interesting things with it. We are going to be having a phase where we have a helicopter, which is a technology demonstration, which, if it succeeds, really opens up a whole new set of possibilities. Sojourner was a technology demonstration, and it was so successful that it has resulted in this a whole series of rovers that we've had on Mars as a result. And then when we have this helicopter phase, there's a lot of interesting interactions with the rover. We have to go select a site. We then have to deploy deploy the helicopter from the rover by lowering it onto the surface, but we have a very limited amount of time when we actually have to drive away, because once the helicopter is disconnected from the rover is no longer charging the helicopter. It has to have its solar panels unshaded to be able to charge. Otherwise, it's not going to survive. So that drive is actually a really important drive, because we have to unshade the solar panels. And then we drive far enough away from it, which is 100 meters, so that we're, ensuring that whatever the risk there might be from a technology demonstration doesn't impact the prime mission. But we're close enough that we can use our cameras to observe the helicopter, and it also has cameras on board so that it'll be able to take images. So that's a really interesting aspect. And depending on how the helicopter does, uh, I think there could be what we do beyond that. It would be open to some discussion. And then as the mission continues, we'll be collecting these cores, but we could continue for as long as uh, there's a scientifically interesting targets to find, which in the case of Curiosity, we're still continuing. And Opportunity, which was a 90-day mission that ended up lasting 14 years, right? You can go for a really long time. The difference in Perseverance and Curiosity are they're nuclear powered. So there's a decay in that nuclear rate. So you do have some limited time horizon beyond a certain point, because the vehicle just has so much lesser charge on what it can do. But it's far into the future. So I have a lot of hope for the possible things we can do in the future. In fact, what we call the extended mission is some of the most interesting time, because once you've met the prime mission goals, you can then start to take a little bit more risk and deploy new technologies. We actually update our software, which is a really interesting thing we do, because the rover has to always be in communication with Earth. It's like trying to install a new operating system while still maintaining all the communication and aspects that you have to. We put new capability on the rover when we do that. We did that with Curiosity. In fact, some of the technologies, like autonomously selecting features and rocks, was something we put on an extended mission in Curiosity. So I particularly think that there's a lot of things that we haven't thought of that could come in the future. And in fact, the people who might be driving these rovers, as was the case with the Mer rovers, they might be in high school right now. So there's a lot of possibilities.
Very symbolic. You just mentioned about the rover moving away 100 meters and ensuring that the helicopter is going to be safe and secure where it is, or in a way protecting it. We spoke about something very similar earlier when you spoke about rover drivers, and that's, I think, what you guys are doing to the next generation as well. You all are there, but guiding them to move on. So I think that's a very symbolic piece. Probably a rover handing over to a helicopter for future missions.
There's a lot of possibilities. The rover, the next mission could either be, or a future mission could either be a helicopter that has sufficient weight, can carry a payload mass of a few kilograms, so it itself is an entire mission, or it could be a scout where it works in coordination with a rover and is scouting out potential areas to go or mapping out the terrain ahead. So it could either be a coupled mission, which I think is really interesting. We really are moving into this era of multiple uh, robots, whether they be flying, driving, submersibles, various different aspects of coordinating robots together, doing the scientific investigation.
Does this mean with this mission for you, Vandy, you start getting really busy now? And how do you plan your day? Just trying to understand your workload and how does this work for you? Because you are getting to that stage of the landing where things are going to get pretty exciting.
Yes, so this is such an incredible time. I really love this phase of a mission because it brings the entire team together with a lot of excitement. So this next couple of weeks are going to be very interesting. We really have a lot of training we're still doing and checking all of the last minute boxes, and then we go on Mars time. So starting February 18th, I'll be operating on Mars time. So working in that time, and you really try to have your circadian rhythm, as we call it, adjust to that. Otherwise, if you keep shifting, it's sort of like having a jet lag every day. And we'll be working in that phase where every day you get to see new things come from the rover and are working on whatever it is that Mars throws at you. So very excited about that. So we'll have 90 sols of Mars time operation starting February 18th.
When you say you'll be switching to Mars time, do you have a Mars clock watch? How do you, because it's 38 minutes. I'm just trying to understand how.
Oh, yes, there is. In fact, there's apps that anybody can get too. But we do have Mars time clock, so you can both see the Earth and Mars time because you very much want to know what time it is on Mars because our schedules are driven by the Mars time and our the times that we are in the operations room where we're controlling the rovers from is all coordinated based on that.
Vandy, there are so many people listening to you now, and there are a lot of college, school children who listen to us. In fact, you're going to get a lot of people who are going to listen to you and now wake up and I want to be a Mars rover driver. Now, your journey was very interesting as well. You started with electrical engineering. You got into certain other missions as well. You tested robotics in the Arctic and in the Antarctic, which is absolutely stunning. You were into uh, designing of software as well. Now, all through this time, for young kids listening to you, Vandy, and just using yourself as an example, what message would you want to give them? Did you choose the path and plan according to the goal, or did you follow something that excited you and then moved in that direction?
Yeah, and thank you, Håkon, for doing this because I think it's so incredible that you're trying to reach the students because uh, they really are, the hope for the future, for things to come that we haven't imagined. So that's really incredible. In terms of what students can do, I think it's important to invest time in understanding the fundamentals because once you do that, you can experiment with what it is that projects that really fascinate you and apply those. And that's something that doesn't go away, no matter sort of what you're approaching. Initially, as you say, I grew up around airplanes, and I was very interested in them, but I didn't have as much exposure directly to robotics. But I followed what was the most interesting to me at that time and tried to really delve deeply into it. And that opens up other doors, and stay open to those possibilities. And you will eventually discover something that really uh, sparks your imagination and says, this is really what I want to do. And even if it seems really far away, if you keep following what's the most interesting thing available to you and working hard to understand it, it leads to more and more things. I really truly believe that if you follow that process, you will be doing something really interesting, potentially in an area that you might not imagine now, that that'll open up to you if you stay open to the possibilities.
That's a very inspiring message, Vandy. And have you ever considered, after all this time with driving on these different terrains, coming up with a book on all your experiences and putting this all together for us to follow, read, watch, if we want to know more about these things?
That's that's an interesting idea. Um, I haven't thought of that yet, but maybe you planted the seed in my head, and maybe there's somebody out there who's interested in discussing how that might unfold. I do sometimes, share on social media as time allows. Certain parts of parts of our mission as we're unfolding, and so I'll do that sometimes on Twitter or Instagram, and through outreach with our education office at NASA JPL.
If there is a book and we get to know more about these experiences, I can assure you, you will be having a lot of people who are going to be queuing up to listen to all these experiences, because there's nothing better than listening to unearthly experiences that are factual. Because we all have unearthly experiences, but unfortunately they may not be factual. But in your case, it's specific, factual, and scientific. So that lends so much more credibility to it. And I have to tell you, I'll give you a little bit of a surprise here, and I speak to some of my guests proudly when I talk to them about this. So as soon as Perseverance lands, Vandy, there's only going to be one podcast available on Mars. And that's going to be Indian Genes. Do you know why?
No.
So when NASA came up with this contest about a year ago, where you could put your name and your name would be on a chip on Perseverance going to Mars, we actually put the Indian Genes podcast and sent it, and it got accepted, and we got a small little boarding card. And now I proudly go around telling everyone that Indian Genes is going to be the only and first podcast actually on Mars.
Oh, that's great. Yeah, in fact, that's so great. I did not know that. We do have 3 chips that we put all of the names that everybody submitted onto the rover, and they will be landing on February 18th.
Vandy, once again, thank you so much for your time. It was an extremely engrossing, informative, very interesting conversation with you. We've learned so much more about what's going to happen, and I'm sure all of us here wish you and the entire team a safe landing. It's going to be amazing for you witnessing it at the control center, and our wishes and prayers are with all of you.
Thank you. I enjoyed this a lot. Thank you.
So to all our listeners, this podcast was created on Hubhopper Studio. So if you wish to start your podcast for free, visit www.hubhopperstudio.com. Hubhopper is India's leading podcast creation platform, and you can start your podcast with Hubhopper Studio and get your voice heard across platforms like Spotify, Ghana, Google Podcasts, Wink Music, and much more. Do click on the link in the episode description or visit www.hubhopperstudio.com. Once again, thank you for listening, and do stay tuned for many more very interesting episodes.